Hi, I'm Rex from the University of Illinois Urbana-Champaign. Today I'm presenting our paper, XMem Long-Term Video Object Segmentation with an Atkinson-Shiffrin Memory Model. Video Object Segmentation, or VOS, is a task of checking a mask from the first frame to the rest of the video. This mask is class agnostic, meaning that the model has to potentially deal with novel objects during test time. There are a lot of prior works in this direction. One of them is recurrent model. It uses the first frame input image and mask to first initialize hidden state. This hidden state is then used by a network to segment any new given frame. The network can also update the hidden state so as to adapt to any appearance changes of the target object. And for recent state-of-the-art approaches, they're mostly attention-based, which means the input is first appended to a memory bank. Then, the network will use attention to read features from this memory bank and use that to segment any new given frame. The segmented result can be appended back to the memory bank so as to enrich its representation and to represent appearance changes. However, both of these approaches have shortcomings. For recurrent models, since it is continuously forgetting its hidden representation, that would manifest itself as a vanishing gradient problem, which means it actually performs poorly in the long term. And for attention-based methods, since we are continuously appending new features into the memory bank, both the memory and the computational costs would increase over time. That is obviously undesirable and would actually be infeasible for longer sequences of, say, a few hundred frames, or for sequences that are longer than a minute long. To solve these problems, we take inspiration from the human memory. The Atkinson-Shiffrin memory model theorized that the human memory is made up of three components: a sensory memory, a working memory, and a long-term memory. Our model implements these three types of feature memory instead of using just one. The feature memory is the fastest reacting. It is also locality sensitive, which means it gives positional prior to our model. It is implemented with the conv GRU. For working memory, it contains high resolution features, and they can be used for query key value matching, which is attention matching. Because of its high resolution, we only keep it for a few seconds. The long-term memory, on the other hand, stores compact features consolidated from the working memory. Because these features are already compressed, we can store them for a long time, say for tens of thousands of frames, without running into any GPU memory problem. Our model achieves great results on both short and long-term datasets. We achieve state-of-the-art results on 3 video object segmentation benchmarks, with average video lengths ranging from 100 frames to a few thousand frames. Our model is also quite fast, running at above 20 fps. Here, we show a qualitative result of our method. The user first annotates the mask in the first frame. Note that the Coca-Cola can is annotated with a green mask, while the Dr. Pepper can is annotated with a red mask. After annotating the first frame, the user can then start the mask propagation process. While the mask is propagating, allow me to introduce to you our project page. The link is shown on the slide. You can find our code, more qualitative result, and also an interactive GUI demo, which was used to produce the video that you're seeing on the left. You can also use our GUI to either test the performance of our model or just to segment your own videos. Now, going back to the video on the left, several thousand frames has passed while both of those cans has been occluded by the tower. Yet, as you'll see later, our long-term video object segmentation model is still able to pick up those two cans with an accurate segmentation. More information can be found on our project page.